I am Craig Kibukamusoke of Structured Environment, a structural engineering consultancy based in the UK and Japan. Thank you for joining me on this webinar on the Eurocode design procedures on a project in the EC1 area of London that we have designed and analysed in Midas Gen. As we go through the project, I will touch on an overview of the project, the challenges we faced, how Eurocode was used, how we applied this all to our scheme, and the results in Midas. First, a brief overview of the project. Currently, in the UK, and in London in particular, house prices are extremely high. There are also many historic buildings in areas where planning laws make it difficult to demolish or alter. As a result, in recent times, there has been an increasing trend to extend or remodel existing buildings. This is because it is cheaper to construct additional space than to sell and buy a new property. Here are some examples of typical extensions. The picture here on the right shows a row of houses that have all been converted or extended into the loft. The style of loft conversion shown here is typically of timber frame construction. As well as extending upwards, basement extensions are another popular option. Here is a picture of a basement that we have designed, taken during the construction phase. Here you can see the reinforced concrete underpins being installed in 1 meter sections, supporting the existing building above. You can also see the reinforcement bars sticking out to be connected to the next underpin. And over here you can see the finished and furnished basement. However, due to labour costs and the laws involved with underpinning shared walls in adjoining properties, construction costs are relatively higher than those associated with above-ground extensions. In this case, the existing property is a 5-storey masonry building with solid roof and floors. It is originally built in the 1600s as a warehouse or factory. This is an image of the building. In recent times, it has been converted into serviced apartments, which is when we believe the solid floors and roof were installed. The building is located in an area traditionally known as the City of London, and the site itself is between the legal and commercial districts of London. The property abuts a luxury hotel and neighbours an embassy and office buildings. With this background, the client in this case is a developer who has acquired the air rights above the existing building for development. The proposal is to build a 2-storey upward extension to the existing property, creating a penthouse maisonette. As the construction is due to begin shortly, we have prepared some superimposed images of the proposed structure as shown on the slide. Here is an impression of what the structure will look like at existing roof level, and here is an impression of what the structure will look like from street level. As with any project, we face some challenges. Construction prices in London are very high, with an average building cost per square metre being $20,000. As it is also a densely populated area, consequently, maximisation of the livable floor space and flexibility of the internal arrangements were essential to ensure the client could obtain his desired profit margin. In order to obtain planning permission from the local authority, we had to work with the condition that the proposed extension would not affect the rights of light for the neighbouring buildings. An independent survey produced results which required each additional level to be offset from the facade of the floor below, and also put a height restriction on the proposed development. The finished floor-to-ceiling heights affect the perceived comfort of space, and this impacts the sell-on value. Here you can see the proposed architectural elevations. One of the main challenges we faced was keeping the structural member sizes to a minimum and ensuring that they are light in weight. In this way, the structure was kept both efficient and light enough to install without heavy cranes. The design codes used in this project were the Eurocodes. As with most codes, Eurocodes split the actions, or loads, into two main categories: dead, permanent loads, and live, variable loads. Dead loads are derived from the bulk density of a material and determining the volume of the material, typically represented in kilonewtons per meter squared as a uniformly distributed load. Live loads are displayed in a table within the Eurocode. The values of the live loading are categorized depending on the proposed occupancy of the building. These two are commonly represented as kilonewtons per meter squared. In the Eurocode, horizontal loads such as wind loads are classified as a live load. For example, a value of 0.6 kilonewtons per meter squared for a standard timber joist floor is usually adequate. However, for our project, we allowed for a higher spec floor, so we used a loading of 1 kilonewton per meter squared. And typically, for a self-contained dwelling such as the proposed, a value of 1.5 kilonewtons per meter squared is adopted, as shown in the screenshot. For the scale and location of the EC1 project, dead loads, live loads, and wind loads were modeled on the structure. These loads are then applied to the structure and adequacy checks are then made. Ultimate limit stress assesses the strength of the structure and ensures that the structure does not fail under ultimate forces and moments. For these checks, factors are applied to the load. Within the Eurocode, a safety factor of 1.35 is defined for dead loads and a safety factor of 1.5 is defined for live loads. Service limit state assesses the serviceability of the structure, ensuring that the structure does not cause damage to the finishes, impair the occupation of the building, or create discomfort to the occupants. From our perspective, for a residential building, we aim to limit the deflection of the floors for comfort and limit the sway of the structure to prevent cracking to the fabrics. Often in London, where masonry is involved, care is needed to make sure deflections of supporting members are kept to a minimum to prevent cracking to the brittle material. A maximum deflection limit of span divided by 360 is adequate for a steel beam supporting masonry, whereas for a steel beam supporting a timber floor, as is with our case, a maximum deflection limit of span divided by 270 is adequate. In addition to this, lateral sway in the steel moment frame, for example, is limited to height divided by 300. With this in mind, within the guidance of the Eurocode, these factors used in the checks on the structure allow for a design life of 50 years for a dwelling. We began to develop the scheme within Midas. One of the requirements from the local authority was for the proposed window locations to follow those in the existing building. To ensure this, and to create the proposed flexible 5th and 6th floor plans, we produced a structural scheme aimed to allow full width openings in the south facade and frames that minimize weight. The proposed building is clad with prefabricated wall and roof panel system. We therefore proposed a series of steel moment frames to be introduced at approximately 3.5 centers. This allowed the timber floors, wall and roof panel systems to be simply installed. In the longitudinal direction, braces were introduced in between the bays of steel frames at both levels to carry sway load. Apart from habitability, the limitation of longitudinal sway was vital to ensure the structure does not load the abutting hotel. The steel moment frames were used to distribute new loads onto the masonry perimeter wall only, without loading the existing solid roof, as the strength of the existing roof is difficult to verify. The steel frames were designed to provide lateral stability when wind loads act upon the structure. In plan, we designed a timber joist floor spanning between a series of closely spaced 203 by 203 universal columns as beams. These floor beams are then pin connected to the steel frames. The end bay towards the rear of the property was required to be of smaller 152 by 152 universal column sections to allow for enough space for the staircase to be extended upwards. Lateral sway into this bay is also carried using 10 mm by 150 mm steel cross braces. In accordance with the conditions set by the local authority, we had to set back the 5th floor facade by 200 mm and the 6th floor by 510 mm from the existing brickwork. To achieve the setback above, to achieve the setback above and still keep the load central over the perimeter wall, the ends of the main beams are cantilevered. The effect of this creates a staggered frame as shown. Also shown in the detail is the bearing pad we used to connect the frame to the perimeter wall. To assemble the model, we chose to build it in Midas by importing the AutoCAD file of the 5th floor plan and transposing the plan to create the other level. Midas allows simple importing of AutoCAD data. Once we had the model built in Midas, we began assigning the beam end releases, defining which connections are to be fixed or pinned, and assigning support points as shown in the screenshot. We then began to apply the loads onto the structure. The wall panel system was input into Midas as a line load and applied onto the perimeter beams. As shown in the screenshot, Midas's floor loads function was used to model the timber floor and roof panels. This function allows the load to be distributed and, when applied to the structure, shows the span direction of the load. In this function, you can also assign how much of the loading is dead or live loads. In the story function, Midas automatically generated the story data and allowed us to input the relative levels of each floor from the ground level. The distribution of the wind load is dependent on whether the floor diaphragm is considered or not. By selecting Do Not Consider under the Floor Diaphragm tab in the analysis, the wind load is calculated and applied to each individual frame. This will then show how the frames act individually to the horizontal loading. Obviously, in reality, since there will be a plywood floor, there will be a diaphragm to spread the horizontal loads between the frames. However, for the purpose of modeling, we wanted to analyze the strength and lateral stiffness of the individual frames. The alternative would be to select Consider, and then a consolidated wind load is applied at the center of the structure and relies on the diaphragm action to spread the loads to each frame. The longitudinal wind load is taken axially by the beams and transferred into the brace elements. We use Midas's built-in wind loading generator to apply the wind loads to the structure. At this point, you can select to use the wind load case in accordance with the Eurocode. When calculating wind load, the Eurocode allows for nationally dependent parameters to be input. So using wind maps, altitude, and geographical data, we determined the wind speed. By inputting this information into the wind load generator and identifying the terrain roughness type, Midas will calculate the design wind load and apply it to the structure, referencing your story data. Before we can analyze the structure, we wanted to create a few load combinations. We used the steel automated combination generator in accordance with the Eurocode, with safety factors of 1.35 for dead load and 1.5 for live load. This generator references the Eurocode and applies the combination factors to reduce design values when they act together, creating different load cases. A particularly useful design tool is the envelope combination feature. An envelope combination automatically selects the worst case combination for strength and for serviceability. When we when we are assessing the lateral and longitudinal deflection, we set the deflection limit for column members to height divided by 300, and in assessing the vertical direction, we set the deflection limit for beam members to span divided by 270 for floors. I will now launch the model in Midas. Okay, so here you can see a wireframe of the structure. So one of our main concerns was ensuring that the new loads of the structure would then be spread evenly around the perimeter of the wall. So we had to assess the reactions at each sort of footing that stuck out. So we had, earlier I showed you the projecting bearing pads for each support at the end of each frame. Here you can see that our largest reaction comes towards the rear, the second to last frame. Let's pull up the value. So we're looking at 215 kilonewtons. That's ultimate. That's 152 working. So as a representation, you can see that a lot of the loading that is coming down. We've tried to spread it out, so you've got 100, 100, 100, 100, 100, almost 100 there, and a similar scenario on this side. And as expected, these end ones are going to be significantly less than the central frames. So this helped us ensure that we had only had to design maybe two types of bearing pads, ones for the larger loads and ones for the edge ones that are slightly smaller. This helped keep things simple during the construction phase. One thing we had to bear in mind is that in the existing building, they had large glazing here where the staircase comes up, and a part of one of the conditions set by the local authority was for that to be continued into these additional 2 stories. So one of our frames could not be complete, so we've got a half frame here. We'll just highlight that. This is our half frame. So what we did here to make up for that and bring in some stiffness here, particularly at the top where we would experience the most amount of deflection from the base, is by bringing in these sort of cross beams here. So when the structure would move, this beam would then be in tension and bring some stiffness back into this frame. And if the wind load then was applied in the opposite direction, the same thing would happen here with this cross beam. We tried to also bring back some stiffness as well by having another column here, taking out some of the moments, lateral moments, the moments due to lateral forces just after the intended glazing section. However, everywhere else seems to have full frames that have come in, so we're usually okay there. So if we just show what the lateral sway looks like. only actually talking about millimeters now. And so the most amount we're looking at is just under 6 millimeters, and that's about towards the center of the structure, which makes most amount of sense. Particularly, let's see if we can load up any of the display any of the loadings, particularly the wind loading, and see if we can get there. So here you can see values. So a lot more is happening here. And also what Midas tends to do is it will show the absolute deflection. So if this frame has been deflected by 2 mil and this frame has been deflected by 3 mil respectively, it will represent this as being deflected by 5 mil because it takes into account that being moved, being pushed, set back that away as well. So it makes sense for this to be in the middle, slightly more deflected. So we're all okay with that. And regards to if we can look at how this is performed, so we've got the columns on a. So look at the vertical deflection. So if we pull up the steel code check, and we're checking each member against the steel code, so against Eurocode, check the graphic. Here it'll pull up a quick calculation sheet, and it will tell you the member you're looking at, some properties of the member, and it will tell you the section size you've chosen, and the length of the member, and then the forces that are being applied to the member, the brace length, and then you start to look at the results. So particularly here, you can see story heights over 300. We're well within the limit. Okay. Now for vertical deflection, where we have a network of beams where we're working around internal arrangements such as internal stairs and possible lift shaft that services the whole building, it's expected for us to have a larger deflection towards the center of this steel grillage, if it were. And we're looking at the worst case deflection of 6.7 millimeters, which again, if we were to pull that up, let's actually pull up all of them. So these are all the beams that we've used for the majority of beams that we've used for the floor, and check those up against the steel code check in the graphic form, and it's highlighted the worst case member. That happens to be 182. I think that's a short member. Well, that's a long member. Let's pull that up. And for this one particularly, we had to change the deflection limit, partly because it's such a large span, and it's a pin-ended span, and it's only servicing as a terrace. So we allowed for the terrace to be slightly more bouncy than we would normally allow for an internal floor. And here you can see it's within the limit. Whereas if we were to run the steel code check for internal floors only, internal beams only, so taking those sort of out of it, we can see what's the worst case beam. Okay, section 108. What's that beam? How is that performing? Span over 270. Again, in this case, it's relatively more within the limit. It shows you shows you how it's performing in shear resistance, buckling, bending, axial. So this is also very useful. Another thing we found, which we enjoyed analyzing, was when if you highlight all the members, say that have got your section 3, and you run the steel code check, you're able to then compare the results of each member. So you've selected that, and then you say you want to check it for bending, for example. And here you can see which members are outperforming others, and which ones are possibly might need a new section size to perform better. In this case, because we were quite squeezed for head height and space, we had to stick with the same section sizes, and for ease of installing and making the construction phase a bit more simple, we didn't change the section size for that particular member. However, it could easily, in another scheme, you could easily, for that beam, choose to put in a different section, and then you can probably arrange to have the rest of these beams being used as a slightly lighter section. We found that tool very useful. Another tool that we frequently use, particularly in designing beams and making sure the sections were as economic as possible, particularly not just in the weight of the steel, but in the dimensions of the steel, so particularly the steel depth, and for the beams and steel column thicknesses, so they don't project too much into the room, keeping that wall thickness as thin as it can be to keep your basically maximize your floor space. You have this steel optimal design. And steel optimal design is a form of steel optimal design is a form of iteration. So you can then input in your values. So D1 will be the main dimension you wish to limit your section to. You can put in the shapes of sections that you wish for it to search through, and then the code of the sections that you're working to. And it will grade each member out of 1, 1 being the most economical, 0 being the least economical. And we found it very useful because you could then go through and select each member that you wish to analyze and try and find a better section that would, perform against the steel code check adequately and still fit within your requirements. However, for ease of one of our problems we found was during the construction phase, we due to the location of the property being in a busy part of London, assembly of the frames had to be rapid, and we were confined to a small construction site. So you had to ensure you had a minimal impact on the local residents and the traffic as the materials are brought onto site and assembled. So we had to make sure assembly was as quick as possible, and the delivery of of materials on site was rapid. So if we could, in areas such as this beam, for example, so ST3s, ST3s are our brace members that we have at both levels to stop lateral sway, longitudinal sway, sorry. These could have easily, according to this steel code check, COM says it's at 0.125. That means it's not very economical section for the loads being applied to it. However, for the ease of installing and for the connection details and designing that point, connecting them all into place, for the sizes of the other beams, we found this to be a very easy section to use. So that's why in that case they have been over-designed. As goes for in this case where we've got the flat bars have been brought in just to provide additional stiffness to that rear frame, just so it doesn't sway too much whilst we're butting against the neighbouring hotel, and particularly because we've reduced the section of that rear frame, reduced the steel section to allow for the stairs to come up, so we had to reintroduce some lateral stiffness from another method. So the steel code check says that those have been overly designed. These have been designed actually as tension-only members. So they're only ever working, when in the design case, they're only ever working in tension. So if the wind blows in the Y direction, only those ones in the tension would work and would represent in the results. If they were blowing in minus Y direction, the opposite would happen. But again, for the ease of the connection details and allowing edge distances for bolts, etc., this is why we chose this particular size of member. And another thing we had to assess was, whilst in the construction phase, the client wished for each. We couldn't just bring up, 6-meter long beams, or let's find out how big this guy is. No, almost 8-meter long beams. Client didn't want that. He particularly wanted them to be in as small sections as possible, preferably having corners and any fixed connection moment connections being prefabricated, so you're just bolting splice connections at mid-span, or 1-meter sections into beams. So we had to ensure that these connections would be adequate. So we had to use the tool beam detail analysis to assess the moments during the moments within the beam, to find an adequate location for these beams to be spliced, so that we could assess whether this is an okay location for the forces, because we have wind load and vertical loads. You might be experiencing axial loads coming through the beams. You've got brace members coming down, being supported on beams. So we had to make sure that the location wasn't at a vital point within the section for us to then put a brake in. This is quite a useful tool, because you can actually see how the beam is performed, the loads actually on the beam, and how it's performing, so where your maximum deflections are at. The shear forces, the bending moment diagrams, and these can all be used for different load cases. For example, so this is showing what the deflection in the beam just under wind load in this moment frame. So thank you for listening to this webinar. I hope it's been useful. This is a fairly simple structure, but we've had to work with fairly tight constraints. But it's been a great opportunity to work on and learn to use Midas, and I hope and feel like this is a useful way for you to see how to think about using Midas in a practical sense, not just theoretical. My name is Craig Kibukamusoke. I'm a Structured Environment. I hope this has been useful. If you have any questions, I'm sure Midas will give you a way for your questions to be answered and your queries to be heard. Thank you again. Goodbye.